let's go ahead and take a look at our logistic model. This one would be very painful to have to do by hand, but recall that here in this model we had a growth rate parameter of 0.1, a carrying capacity of 4 elk, and I say appropriately scaled. This could be 400 or 4 million or 4,000, whatever. We don't want to say that you can't have 0.2 elk because it could be in hundreds or thousands, in millions, etc. So to sketch this guy here, I'm going to come over to my slope field and just type in 0.1y times 1 minus y over 4. Before I press enter, the one thing that we should notice is that we're going to have equilibrium points at both y equals 0 and y equals 4. So that means that we should notice horizontally that our slopes are going to all be the same. That means we're going to have rows of very similar vectors since this only depends on y and not on t. This is an autonomous differential equation. If I press enter now, let me go ahead and clear all the curves. Looks very boring, right? Because first of all, I am looking at a window of populations from y equals -1 to 1. I can't even see the equilibrium point in there yet, but I do see that right at y equals 0, those neighboring slope vectors look very, very flat, which makes sense. So let me change my t to go from, maybe not, if this is years, maybe I want to do 10 years. And maybe for y, I want to go from 0 elk. Let me go from -3 elk. And I'll tell you why in a second, all the way up to 7 elk. So the first thing that we see here is I'm going to change my value of t just because these slope vectors are kind of flat and boring. So let me go up to maybe time 20. There we go. We kind of see more curvature in here. But you see that right at y equals 0, if I pick an initial condition, I could click on 0, 0, but it's not ever going to be able to look at this ordered pair here that pops up. I'm never going to be able to get it close to 0, 0, as close as I want. So I'll just type the initial condition in. Well, there you go. So if you have 0 elk, you're going to have 0 elk for all time because when y is equal to 0, the rate of change is always 0. So notice that all the slope vectors at y equals 0 are similar. Now maybe I want to also consider, what if I start off with a population of 4? Well, if y is 4, I'll get 1 minus 1, which is 0, and that's going to give me a 0 slope as well. Well, there you go. So if you are at your carrying capacity, you're going to have births and deaths, but you're not going to have a growing population. I'll just click in here to show what that curve looks like. So you have this exponential growth, but it takes a while to pick up, and that could just be due to our slow growth rate. But let me go ahead and change this maybe to time 60. And there we go. There we see that logistic curve. That's where this model gets its name. It's called a logistic growth curve. So you see that the population starts to blow up, but then because of the carrying capacity, because of limited resources, the population is still growing but at a decreasing rate, and the population flattens off as we approach the carrying capacity. Initial conditions above y equals 4, we see that those decay, right, because we're overpopulated, we're beyond our carrying capacity of the environment, so the population is going to want to decrease back to y equals 4. So the equilibrium points very much act like asymptotes. If I pick anything here, I know I can't have negative populations, but what we should see is that the population in that case would decrease infinitely. You can also experiment with this and change this to see, okay, well, what would happen if I doubled the growth rate parameter? Well, that just means that growth is going to occur faster. That shouldn't change the equilibrium points, but watch what happens to this point right here. I'm going to leave my cursor right there, which is about the inflection point, where we go from concave up to concave down. And now you see that that point is shifted over here. Well, that makes sense because the population growth rate is much faster, so we should approach our carrying capacity faster than if we had that rate of 0.1. So that looks like an S, but it's almost as if you horizontally stretch that S. If I make this 0.5 to really make that clear, look how fast it reaches its carrying capacity, and look how fast these things happen. And that should make sense because mathematically what we're doing is we're scaling the rate of change by a bigger factor. If I make this like 10, which is just insane growth, that S is very, very compressed and growth occurs very, very rapidly. We'll talk more about what all these little features mean in here. These are just kind of some models that they have built in, and we'll talk more about the numerical solution table as we go. One last key point here is that in general, a good strategy for determining what a slope field will look like is to first consider the equilibrium points of that model. So, for instance, given a differential equation such as dy dt equals, we'll just say something like 3 minus y. Well, if I first look at what the equilibrium points of this are, and I set this equal to 0, and I find out that y equals 3 is an equilibrium point, what that already enables me to do in this sketch of this slope field is that I know that if y equals 3, 1, 2, 3, that my slope fields for y equals 3 will all be 0. And now, because this is autonomous, we know that it doesn't depend on t, so t will not influence the rate of change. But when y is bigger than 3, then that's going to give me 3 minus a bigger number, which is going to give me a negative slopes here, and when y is less than 3, positive slopes here. So that kind of already gives me some insight into what I should be observing, something similar to this. So first start off with those equilibrium points. Even if there are some, a lot of times there aren't any equilibrium points, but at least it gives you an idea of what's going on. So that's it for this video on slope fields. In an ensuing lesson, we're going to get into Euler's method, which is an explanation for how this applet actually produces these solution curves.